Yes, then.
All right, then, yeah, welcome back to today's session, which is a continuation of what we started discussing and basically recapping yesterday. So yesterday essentially was a recap of laser physics as to get you prepared to the topic of free electron lasers, which is a very special kind of lasers. And then today we will touch upon a few alternative light sources to generate short wavelength radiation, so extreme ultraviolet and X-ray radiation. Uh, yeah, to in view of getting to the XFEL, the X-ray free electron laser concept. And then next step towards free electron lasers is a recap on or an introduction to synchrotron radiation. As you will see that synchrotrons are, let's say, the predecessor technology of free electron laser technology. But just as a to connect to yesterday's presentation, this is one of the last slides that we were looking at. This was a very simple rate equation model to describe laser activity, which essentially describes the active medium in a laser that is described by the main figure of merit in the active medium, which is the inversion. The inversion, that's the difference in population between the upper laser level and the lower laser level. And in positive inversion means there is more population in the upper laser level than in the lower laser level, which is the prerequisite for amplifying radiation that hits the active medium by stimulated emission. So we want stimulated emission, this transition from the upper laser level down to the lower laser level to be the dominant process, so to have a faster rate compared to our enemy, which is spontaneous emission, which depletes the inversion by spontaneous emission of photons, which is incoherent and thus the unwanted process. So inversion has a rate equation, and which is coupled to the other main quantity, which is the quantity describing the radiation field. That's the photon density, P. And those two quantities are coupled together. They are described in this very simple, in the simple most model in these coupled rate equations. And the rate equation for photon density essentially can be written just as a term proportional to the gain, which amplifies the light, which enhances photon density, and another term, a loss term, which depletes the photon density. And depletion happens through losses, and the main source of losses is the transmission of light through the output coupling mirror. Because in the end, we want to get a beam out of the laser. So we need to extract photons out of the laser to get a beam, and that naturally causes losses. So already from this simple equation, we can formulate a condition for lasing, which is gain has to exceed losses for lasing to happen. And another condition for achieving CW lasing, CW stands for continuous wave lasing, meaning lasing in steady state conditions. All time derivatives are zero. From setting the time derivative to zero, we automatically get the result that either the photon field is the photon density is zero, so no lasing at all, or gain equals losses, which by this definition of the threshold inversion means that the inversion is locked to the threshold value. So that is kind of a surprising result that no matter how strong we pump the system, like how strongly we try to shuffle up population from the lowest level in the system into the upper laser level, the inversion, so difference of population up and down, is always locked to this minimum value, this threshold inversion value. And how does it come? I mean, where does the energy go if we now pump in a lot of energy and try to increase the inversion? Well, naturally, by this coupled rate equation, the more we try to increase population in the upper laser level, the more stimulated emission sets in and again depletes the population in the upper laser level. So all we achieve by pumping harder is that we increase the stimulated emission rate, which again depletes the upper laser level up to this threshold value. But that's exactly what we want. Yeah, we want to pump hard and get a lot of photons out in the laser mode by stimulated emission, and in this way we get an intense laser beam. Another consequence of this condition for CW lasing, that the inversion is locked to the threshold value. This we discussed using this figure here. Just as a recap, the figure shows the gain profile as a function of the frequency, which in many cases is quite a broad profile. Then there is a loss curve. Yeah, the losses also have some frequency dependence, for example, given by the reflectivity curve of the mirrors of the resonator. And in a laser resonator, we have a resonance condition, which is given by the fact that multiples of half the wavelength has to equal the cavity length, and that translates into the frequency being discretized into multiples of what is called the free spectral range. The free spectral range is a C over 2L. That's just the spacing between the cavity modes. So that's where lasing can occur. And lasing can occur only in the range where gain exceeds losses. So in the range where the blue curve exceeds the red curve, in principle. But we have just discussed that when CW lasing occurs, then the gain is saturated, is depleted. I mean, gain is proportional to the inversion. That's essentially just given by the inversion. Then the gain is depleted down to the loss curve. Then we have gain equals losses, and this mathematically comes to just one point in frequency where the red curve and the blue curves just touch each other at the position of one laser mode, such that if we now following this argumentation, then draw the laser spectrum where actually lasing happens. This happens in this one point, meaning that the laser spectrum is given by essentially a delta function, so extremely narrow range. We also discussed that since the gain curve is reduced, it's saturated down to the loss curve, but it, of course, is not zero away from the laser mode, so that in this whole range where there is gain, there can be spontaneous emission, which means that there is this broad contribution of spontaneous emission also, which is the bad part we don't want. We want, of course, mostly lasing to occur in this extremely narrow laser mode. But yeah, this interesting result is that from this very simple rate equation model already, we can conclude that by the laser principle, we should expect an extremely narrow spectrum of the laser radiation. Of course, in the real world, this is not a delta function. There is sources of technical noise, such as vibrations of the resonator mirrors. There is noise in the gain profile, in the gain medium, because any gain is pumped by some electrical power supply, which has noise and so on. So if This usually limits the line width of the laser to a megahertz or so in many CW laser applications, but by stabilizing all the relevant components of the laser, resonator, power supply, and so on, it is possible to actually achieve extremely narrowband laser radiation by this principle. Anyway, so this was the discussion we stopped yesterday at. Um, an important component of the laser obviously is the laser resonator, which is given by two mirrors in the simplest case, in the case of a linear resonator. So building a laser depends on having mirrors with high reflectivity to achieve narrow laser modes, resonator modes. The width of these resonator modes are given by Fourier transform. The spectral widths are given by the lifetime of the photons in the resonator. So if you want a sharp resonator mode, we need long lifetime, meaning high reflectivity of the resonator mirrors, such that the photons are trapped in the cavity for a long time. So it relies on having high quality, high reflectivity mirrors. And now, since we want to slowly move up in photon energy towards extreme ultraviolet and even X-ray, naturally the question occurs, do we have mirrors, or how can we build a resonator for these high photon energies? So if we, the usual maybe experimentalist's approach would be check out the web page of a typical supplier of optic components, which is Thorlabs. In many cases, maybe some of you are familiar with the Thorlabs company. Very useful because it also provides a lot of data about the different components. For example, silver coating on silver protected silver mirrors, or even there's an aluminum mirror here, which is UV enhanced. But you will notice that the reflectance is actually very high, like up to almost 100% in a range, or between 95 and 100% in a range from 20 micrometers, which is mid-infrared, down to the visible range, which is in visible range is below 1 micrometer, like 800 nanometers, maybe down to 300 nanometers. This range here is the visible range. We still have decent reflectivities, but then the reflectance drops to very low values at wavelength something like 300 nanometers, or if in the case of UV enhanced aluminum, 200 nanometers. So when it gets into the ultraviolet range, then reflectivities typically for metals, but for any other materials, drop down to very low values. So that's bad news if you want to build a laser resonator in the extreme ultraviolet or XUV range. It turns out that there are tricks to extend the range of where reflectivities still have decent values. For example, by making these multi-layer mirrors, a very typical combination of substances from which to make these periodic multi-layer mirrors is molybdenum silver layers of the thickness of a few nanometers. In that case, by the fact that the index of refraction, even for soft X-rays and extreme ultraviolet light, index of refraction is quite different for these two materials. At the interfaces between these layers, we get some reflectivity, and then by making such a stack of these interfaces, we can exploit interference of the reflected rays, and we can exploit the Bragg condition for constructive interference of these partial rays to achieve rather decent reflectivities in a narrow range of photon energies. So for example, this is taken from this paper here, quite a recent paper actually, where this multi-layer structure achieves a reflectance or reflectivity of like 50% up to 60% at 6.65 nanometers, which corresponds to about 18 eV. So this is already a vacuum ultraviolet, where standard optics cannot provide any decent reflectivity. But 50%, 60% still is not enormous, right? But that's pretty much the best we can get in this extreme ultraviolet range, and only in a rather narrow range, because we rely on this Bragg condition, which defines specific wavelengths and orders, like discrete orders of wavelengths, where constructive interference is fulfilled. Just to mention that nevertheless, although the reflectivity is rather low, these type of mirrors are extremely important in technology. And one of the most important technologies nowadays, of all technologies, I would say, is the technology of photolithography. I'm not sure how much you know about photolithography, but that's a technique to produce very small structures on a substrate. For example, on what is called a silicon wafer. That's a semiconductor substrate that is used in semiconductor industry for producing microchips. And there is, like, on the global scale, a race for producing the smallest possible structures for like semiconductor structures for making the most highly integrated and most powerful computer chips, as all of our modern societies rely on computers and smartphones and highly integrated semiconductor technology. Yeah, the race is to generate yet smaller structures, more integrated structures. I think nowadays the current cutting edge technology is 3 nanometer structure size for making essentially transistors, billions of transistors on a substrate to form a processor, for example. And yeah, if you think about making a microstructure on a surface with a characteristic size of the structures of 3 nanometers, it is very clear. With 3 nanometers, this is about 30 atoms. Yeah, an atom is about an angstrom large. So 3 nanometers is 30 atoms. So we are talking about really like making nanostructures on surfaces at a scale of billions of these to produce a microchip, a processor. Then it is obvious that this is not possible any mechanical means. This relies on optical means, and the technology to produce these highly integrated structures on a surface is photolithography. And since we are talking about nanometer structures, or few nanometer structures, obviously it doesn't work with infrared or visible light. We need a very short wavelength radiation for that. And short wavelength radiation, this is so ideally we would want an intense EUV, extreme ultraviolet laser, or some other coherent intense light source, which is very hard to realize. Yeah, there is no laser or there's only free electron lasers that get into this regime. But for industrial purposes, there is only one other way to produce this nowadays, to produce this intense EUV radiation. And that is shown here. So this is relies on driving a plasma in microparticles, and the best way to produce like a point source of high density plasma is to irradiate a jet of microparticles traveling through vacuum using intense infrared lasers. These are the good old CO2 lasers, which also are being used a lot for material processing. So we shoot with strong, intense infrared lasers on small microparticles traveling through the vacuum to ionize and excite the atoms in the microparticle, to excite the atoms and ions into even core level excited states, which would then by fluorescence, so by spontaneous emission, relaxation would emit short wavelength light. And it turns out that since then the whole technology relies on imaging the information, like the structure on our wafer, which is provided by a large mask. So the structure is encoded in a mask placed here on the reticle stage, and this structure is imaged from the mask onto the substrate. So we rely on reflective optics because like there's no lenses, no dispersive optics available in the EUV range at these short wavelengths. So we rely on mirrors that have a decent reflectivity in the EUV photon energy range. And the only mirrors, we just talked about are these multi-layer mirrors, and the best reflectivity for now is obtained for the specific wavelength of 13.5 nanometers, where the reflectivity is on the range of 70% on every mirror, which means that for this complicated imaging system to image the mask placed here onto the wafer with these, how many is it? 7 or so reflections on the mirrors. The overall light transmission from this intermediate focus here through the whole imaging system onto the wafer is on the order of 2%. So that is quite pathetic, 2% transmission, but that's the best the technology can provide for now. And I just this is from Wikipedia, the information how then the structure is actually is then imprinted on the substrate. It relies on covering the substrate by what is called a photoresist. That's a polymer which by irradiation by the EUV changes its structure, and then by in a second step of etching and other chemical processing, the irradiated parts of this photoresist can be removed and then can be replaced by conductive and semiconductor structures, and in this way the microstructure can eventually be produced on the substrate. But the bottom line is these multi-layer mirrors are very important for technology, for this photolithography technology. Although reflectivities are low, we are talking about like 50 to 70% only in a narrow range, 13.5 nanometers, and we need very special light sources. Like in this case, these are actually tin microparticles that are irradiated by intense CO2 lasers. They explode, get ionized, get excited, and emit spontaneous fluorescence light to produce these sufficient radiation then for this step. This is another view of such a, it's called a tin droplet source, because tin particles are injected into this big vacuum vessel where they are then irradiated by the CO2 lasers. And the whole irradiation step is also quite complicated to get, to get eventually an average output power in the range of 250 up to 300 watts of EUV radiation. That is quite impressive that this high average powers can be achieved from irradiating these little tin particles in the vacuum. But this is needed to have sufficient throughput for like actually using this technology on an industrial scale for photolithography. Just to show a little bit more in detail how this is done. Yeah, so we have this beam of tin droplets passing through the vacuum, passing very close to this large, extremely precisely machined and polished collecting mirror here to collect the radiation. And these tin particles are irradiated by intense laser light, are exploded, highly excited to emit the EUV light. And actually, yeah, it's not only the infrared laser that drives this microplasma, but actually what happens is that there is a first pre-pulse which melts the tin droplets or tin particles into droplets. And actually, it is the beams are shaped such that the tin particles first elongate into these flat pancake structures, such that they are ideally shaped for the main infrared laser light to come and to homogeneously irradiate this pancake and then transform this whole pancake of tin, liquid tin, into a nanoplasma or a microplasma to irradiate radiate of the XUV radiation. So yeah, the mechanism is the laser generates a plasma. In the plasma, plasma means electrons are detached from the core atoms, but still collectively bound to all the positive charges in the plasma, but free to move, such that when the electric field of the infrared laser now couples to the electrons, essentially the electrons are shaken back and forth and constantly hit the remaining neutral and ionized atoms, and further by electron impact, ionization and impact excitation further excite the core atoms into highly excited states by electron impact, such that these highly excited atoms and ions then emit radiation by spontaneous relaxation. And that's the way to produce the light. Quite so astonishing that by this process you actually get 200 to 300 watts of radiation out, but that's the way it works. And you can imagine that an enormous technical challenge is to keep the mirror clean. So there's all sorts of tricks to try to protect these very precisely machined optics around the plasma from the debris that is created, and that would tend to cover and to coat the laser optics. And in the beginning, this was a huge problem. So these extremely expensive collecting mirrors needed to be replaced on a regular basis. I think nowadays they have figured out some ways to protect the mirrors by injecting some buffer gas to protect the surface from the debris. And yeah, anyway, there is essentially one company in the world, at least in the Western world, company ASML, which is the monopolist of building these kind of photolithography machines. I'm just dwelling on this because this technology obviously is extremely important because that's the main driver of our modern technology-based life and societies. there's mainly this one company, ASML, that actually combines all these different components, the EUV sources, the optical imaging systems, and then all the infrastructure needed to run photolithography on an industrial basis. And there's an interesting movie here. I'll share the link where you can learn how EUV radiation is generated specifically for these EUV photolithography machines. Just on a side note, I have to mention that my group, and also together with our host, Shiva Krishnan, we have been doing quite related experiments for many years. What you see here is not a tin droplet, but it's a helium nanodroplet, which is ignited into a cigar-shaped nanoplasma by an intense laser pulse. We were interested in using these helium nanodroplets, which obviously are like very fundamental and simpler types of nanoparticles to study how this ignition of a nanoplasma and how the dynamics and the whole coupling of such a nanoscale piece of matter to a light field, how this works. And I have to mention this, an important paper, an important result that where Shiva Ramakrishnan was the first author and pioneered this this experiment on helium nanodroplets, and we were able to show that actually the ignition of a nanoplasma in helium droplets is very much facilitated by adding, in blue here, you can see we added a few foreign atoms. In this case, it was xenon atoms, which are much easier to ionize. So this xenon core acted as a seed to provide free electrons, which would then couple to the light field, and then by electron impact ionization, ionize the surrounding helium. First in the first moment to produce this cigar-shaped nanoplasma, which then basically expands into the whole nanodroplet and finally ionizes the whole droplet, such that by measuring the outcoming ions, the yield of ions, we saw that actually this is a way to even efficiently produce helium-2 plus, so fully ionized helium ions, like almost alpha particles, just by controlling the number of xenon atoms that we put in the helium droplets. Yeah? You can see with no xenon, according to theory, there is no ignition. And in the experiment, we actually found no ions. And then just by adding a few xenon atoms, we were able to fully ignite this helium nanoplasma. And this we even did in a time-resolved way by applying two short pulses. A first short pulse that forms a first weak plasma in the droplet, but still it's a plasma, it's energetic, so it leads to expansion. And the point is that after a certain waiting time, this is a delay time between this first igniting pulse and a second drive pulse, we could achieve conditions where the density and the size of this expanding plasma was just optimal to then absorb the energy from a second drive pulse, which then further ionized and heated the plasma such that the yield of helium plus and even helium-2 plus was then even optimal at a waiting time, like a delay time of some 400 to 500 femtoseconds. So this was one of the first pump probe time-resolved experiments on helium nanoparticles to show what is also known in plasma physics as the plasmon resonance. This is conditions where by expanding of this nanoplasma, we achieve a characteristic eigen frequency of the nanoplasma that is just resonant with the driving laser pulse and then optimally absorbs the energy and further ionizes the system. This is from the lab. Snapshots. So we have studied this by detecting ions. I've just shown that. We have also studied these systems by detecting electrons and by actually imaging the electrons on a imaging detector in a setup like this. Yeah? We shoot at helium droplets with a laser and then accelerate electrons up by applying an electric field between these electrode plates here. And then we monitor the distribution of electrons on a shot-to-shot basis by watching with a camera on a phosphor screen. And that is the typical images that you would record. So actually, in between these hits, there's many laser shots that don't produce any signal because they just missed a particle. But when this intense, in this case, it was a mid-infrared laser at 3.2 micrometer wavelength. Whenever such an intense laser pulse then actually hits a nanodroplet, then a whole lot of electrons are produced in this expanding nanoplasma, and those electrons then can be projected and imaged on a detector. So this is almost live, like it is live in the lab when you detect these electron images on a shot-to-shot basis. And you can see that like every shot really looks different from the other. And that's because in this type of helium nanodroplet experiments, every helium droplet looks slightly different from the other because the droplets come in different sizes. Also, these were doped with xenon, so the amount of xenon inside is slightly different. We hit the droplets in different positions inside the focal volume of the laser, so the local intensity is slightly different, which also all these effects add up to these shot-to-shot fluctuations. But yeah, you see sometimes a single helium droplet produces a very bright image of electrons. And very recently, also I would like to mention this experiment, which was led by Keshav Sishodia from IIT Madras, who is a senior PhD student and currently at the Eli Beamlines facility in Prague, and actually currently in the lab doing experiments very similar to this one. Again, this was an experiment where we shot at helium nanodroplets with intense near-infrared laser pulses. But in addition to that, we added what is called a high harmonic laser pulse, an XUV pulse, to produce these first seed electrons instead of embedding xenon atoms to produce seed electrons that would then couple to the infrared pulse to drive the nanoplasma here. In this case, we produce these seed electrons by an ionizing EUV pulse in a more controlled way. And in that case, we didn't detect ions or electrons, but we actually wanted to detect XUV radiation emitted by these droplets. And indeed, when we ionize and nanoplasma ionize these droplets, then a lot of XUV radiation is emitted, which was then spectrally dispersed on a XUV spectrometer. And you can see that we see essentially all possible lines, like fluorescence lines emitted by spontaneous emission, both from xenon ions. So these are essentially the what is it called? The Lyman emission of hydrogen like helium. And also we have some emission of the neutral excited helium atoms, but actually the ionic emission was by far dominating. Yeah, so that's our own experiments to produce XUV and analyze XUV light produced by these laser-driven nanoplasma systems. Just to mention that this technology can be extended up to the X-ray range. And a quite common approach nowadays is instead of using micro or nanoparticles to transform them into a nanoplasma, Another approach is to use a tape, to use solid state material, for example, a copper tape here, which is renewed by passing it through the laser focus here by basically winding the tape on these big coils. And so that's essentially a photograph of how such a X-ray plasma source looks in the lab. This schematic you can see here. So there's an intense, so 5 millijoule, quite powerful near-infrared laser pulse, which is focused through the system onto the copper tape passing just in front of the X-ray optics. And then by hitting the copper tape, driving the copper into microplasma in the focus, then even X-rays can be emitted, which are then focused by the X-ray optics on a sample. And then this is a way to do X-ray, time-resolved X-ray experiments using this plasma emission. In this case, it's a copper tape. Also, some other materials can be used. I mean, as you can see from the emission spectrum from these helium droplets, only very sharp characteristic lines are emitted, and very similar spectra you would get from this copper tape. Of course, the positions of these characteristic lines would be a different position, but yeah, this shows that since this relies on spontaneous emission and spontaneous transition between specific quantum levels in the atoms and ions, there's only very little way of controlling the photon energy. Essentially, it comes to changing from one material to another to control which lines are emitted by the material. So yeah, this is a way to produce XUV or X-ray radiation, but definitely it's not the optimal way because we have only very little control over the wavelength, and also we have only and also the intensity of the radiation is rather low. So yeah, I mean here in these tape-driven plasma sources, the laser generates a plasma. Again, the electric field of the laser accelerates the electrons back and forth, and such that the electrons impact ionize and impact excite even the core levels of the atoms, and then characteristic K alpha emission is induced. And yeah, maybe the good news, or the good part about these light sources that are driven by spontaneous emission is that since the spontaneous emission lifetime, if you remember, the lifetimes in the X-ray range were in the range of 100 femtoseconds, extremely short, then this means that if the drive laser pulse is short and the ignition of the plasma is short, then thanks to the short lifetime, also the emission of the X-ray pulse is short in the range of 100 femtoseconds. Which is nice, but in some experiments we may actually want even shorter pulses than 100 femtoseconds. But there is no way of getting these pulses even shorter because we rely on spontaneous emission, which is just given by the Einstein A coefficient. There's no way of compressing these pulses even shorter. Drawbacks are that the photon energy is essentially determined by the material. We cannot really tune the light. Yeah, photon counts. So the intensity is rather low. We're talking about 10 to the 7 photons per pulse, roughly. And yeah, the whole process relies on spontaneous emission, so it's completely incoherent. And yeah, the most intense radiation naturally comes on these characteristic lines like K alpha, K beta lines. There's only like on a much lower level. There's also some contribution at much higher photon energies due to radiative recombination and Bremsstrahlung of the accelerated electrons that impact that collide with ions inside the plasma. Yes, then I wanted to also show a related and another way of producing UV radiation, which is actually a very active field of research and very promising route that is essentially competing with free electron laser pulses, and that's called high harmonic generation. Certainly, many of you have heard about it, so let's quickly review this. High harmonic generation is actually it's closely related to these plasma sources that we just talked about, but it occurs in a more controlled way. And the way it works is that these short infrared pulses, so it's always driven by short infrared pulses from the typical femtosecond laser sources like the titanium sapphire or nowadays ytterbium lasers, which act as the drive. In this case, the infrared laser pulses are focused into a jet of just an atomic gas. So it's no nanoparticles, no micro droplets, just an atomic gas. And what happens in the atoms is that if we here is this three-step model. So let's start with looking at one electron in a bound Coulomb potential well in this bound state, which is represented by this green wave function here. When now the infrared laser pulse comes, and it's an intense pulse, so it has a strong electric field. The electric field produces an electric potential, which linearly depends on the spatial coordinate, on the radial coordinate. So basically, we have a sum of a Coulomb potential well plus a linear potential from the laser field, which creates a finite barrier on the right-hand side in this case, such that the electron in the bound state can actually tunnel through this barrier out into the continuum and fly out and away from the atom until the next half cycle of the pulse comes, which means the electric field reverses its sign, the electric potential is lifted up, and so is the electron lifted up in potential energy, and then is accelerated back onto the atomic core, where it recollides with the atom. And if the intensity is high, the electron is driven far away, picks up a lot of potential energy from the light field, and then recollides at high kinetic energy, such that we get an energetic recombination process. And in this recombination, a lot of energy needs to be dissipated, and that happens by emitting an energetic photon. And yeah, this is the so-called three-step model. That's the classical representation of this recollision process, which is a source of EUV or even X-ray radiation. And yeah, this is another representation showing a short laser pulse. That's the red curve is the electric field, which oscillates a few times. And every time the electron is driven away from the core, from in the electric field of the laser pulse, and then recollides with the core, then an energetic photon can be emitted. So we get essentially a train or a burst of these XUV pulses in one infrared laser pulse. And that leads to an XUV spectrum shown like this, shown here, for different lengths of the drive infrared pulses. So obviously, the shorter the pulses, the higher the order. This process can also be seen as a high order nonlinear optical process, similar to second harmonic generation in a crystal, yeah, where the frequency is just doubled. So the second order of the drive laser, of the driving light, is produced. In this extremely nonlinear process, then much higher orders can be produced. In this case, you can see that the maximum is around the 25th harmonic, but for these very short pulses and intense pulses, then even up to harmonic order 55 or even up to 60, we get radiation produced. And yeah, so shorter pulses usually are much more efficient in producing high order radiation. Photon energies up to the kilo electron volt regime, so up to X-ray, have actually been reached, but there is this fundamental cutoff. There is an upper limit to the photon energy, h nu, which is given for one by the ionization energy, how much energy it costs to even ionize the atom first to extract the electron and then have it recollide, and then plus a second term with this famous factor 3.17 times UP, where UP is the so-called ponderomotive energy, which is proportional to the intensity and wavelength square of the drive laser. So that is the knob that we can tweak to enhance the photon energy. The ionization energy is given by the choice of the atom, but here we have a way of controlling the highest cutoff energy by essentially either cranking up the intensity or even more efficiently by increasing the wavelength. So that means nowadays, most efficient or most efficient high harmonic sources to produce really high photon energies up to the X-ray are actually not titanium sapphire, not the usual 800 nanometer lasers, but mid-infrared lasers in the range of between, let's say, 1 and 5 or so micrometers. And so high intensities are needed, typically in the range of 10 to the 14 or even higher intensity, but actually not too high intensity. So, I mean, why not? Maybe that's a question for you to tell me. Why would you think, I mean, why is it not a good idea to crank up the intensity to, let's say, 10 to the 16 or even 10 to the 17 watts per square centimeter? Then the UP would be very large and we would get to very high photon energies. And I mean, 10 to the 15, 10 to the 16 watts per square centimeter would actually be technically feasible nowadays. But still, it's not a good idea to have these very high intensities for this type of HHG process. Can somebody tell me what the problem is with going to very high intensities? I know that somebody in the audience knows this very well. Jayesh, for example. What's the problem with cranking up the intensity to, let's say, 10 to the 16 or higher? Jayesh, I'm looking at you, even though you don't know it, but are you using 10 to the 14 or 10 to the 16?
Ray Tanuv also.
Okay, Tanuv, tell me. Why not just crank up the intensity and you get X-rays like crazy? Okay, first you need a laser that is powerful enough, but let's say you have a powerful laser, you focus to the smallest spot size to get the highest intensity. What's the problem with going to
Is it
more than
because
10 to the 15?
ionization saturation? Like my ionization reaches the maximum saturation, also the phase matching conditions?
Yes, exactly. What do you mean by saturation?
Like the amount of like it will completely ionize the atom if we have a very high, like if it is like 10 to the power 16, uh it like all the electrons just get out of the atom basically.
Yes.
Yeah.
Yeah, exactly right. So, I mean, we want the electron to be elongated out of the atom, but they should still remain close to the atom such that we have a chance that they get driven back in this recollision process, right? So if the intensity is high enough that the electron is completely ionized away from the core, it will never it will never reach the like recollide back with the core in the next half cycle. And so yes, so if once a plasma forms, then also the optical properties of the medium changes completely, and phase matching, you mentioned, that is no longer fulfilled, and then we get fluorescence emission possibly. Yeah, we get possibly these characteristic lines, but in this case, this high harmonic generation is actually a coherent process, and that breaks down once we fully ionize the system. That's absolutely right. And yeah, so there is some limit as to the intensity given by this plasma filament formation. And also there is unfortunately a quite severe limit to the conversion efficiency. So I think nowadays like a millionth of energy produced in the high harmonic compared to the driving pulse, like 10 to the -6 is, I think, the typical range of conversion efficiency, meaning that yeah, we are typically talking about harmonic pulses way below 1 microjoule per pulse. So that is quite limited. Nevertheless, this is a very promising approach, and this is a way to produce ultra short, quite controlled pulses in terms of photon energy, in terms of pulse duration. Only pulse energies are unfortunately quite limited still. But just to show you one more example of an experiment already more than 10 years ago, but an experiment where they actually managed to produce X-ray radiation. So this is an experiment by the Captain Mornane group in the United States, where by using, I think, yeah, they had quite long range wavelength radiation in the mid-infrared, even 3.9 micrometer pulses. And those long wavelength pulses here were actually then the most efficient to drive the photon energy up to the kilo electron, just about kilo electron volt range. So 1 keV, very broad spectrum, but at yeah, very low pulse energies or photon flux. We're talking about 10 to the 8 photons per pulse at half a keV. But nevertheless, this is an interesting and promising process for producing these short X-ray or soft X-ray pulses. Yeah, also just to so this is mainly about the frequency spectrum, the frequency characteristics. If we look at the spectral characteristics of these trains of XUV pulses, remember, in every half cycle we have this recollision process. So XUV pulses are emitted in every half cycle of the drive pulse, which results in a train of XUV pulses. Of course, a goal in many experiments is to produce one single isolated pulse, because such a isolated pulse would actually be shorter than a femtosecond. This opens a way of producing attosecond pulses. But the question is how to make sure that only one isolated attosecond pulse is produced. And obviously the straightforward approach would be to produce a IR drive field, which essentially only have one zero crossing. So essentially something like a one single cycle pulse, which is in principle possible, but technically very challenging. But so yeah, to show the spectrum that would result from these type of high harmonic generation processes. So if we actually manage to get to a very short pulse regime, yeah, so this is different pulse length and different wavelengths from 70 femtoseconds, 1.8 micrometer, down to only 11 femtoseconds, 1.8 micrometer. That's the pink. Then you can see that this high harmonic spectrum that contains many harmonics eventually develops a very like structureless, broad part of the spectrum. And this is really the interesting part in this particular experiment. So why, maybe somebody can tell me what does it mean in terms of the time domain that the spectrum now contains a large component of just a broad and like unstructured spectral distribution like this. What is the consequence for the time domain? Like measuring the exact time structure of these short pulses is very hard, yeah, because you can see that the pulse structure is even like faster than the wave, than the period, the oscillation period of the infrared laser pulse. So resolving these is very hard. It's much easier to resolve the spectrum. And in the spectrum, under these ideal conditions, we eventually see a broad structureless distribution. What can we conclude for the time structure?
When
Like the
it
pulse
goes
shape.
out.
Very narrow, very small.
Yes, exactly. Very narrow because yeah, spectral distributions and temporal distributions of pulse shapes are related by Fourier transformation. So a broad continuous distribution in the spectral range by Fourier transformation translates into a very narrow, like delta shaped distribution, and that is then indicative for exactly this case of producing an isolated sub-femtosecond or attosecond pulse. So that's, I guess, that what Jayesh and many other people would like to see in the lab, that your spectrum would develop into this very broad and continuous spectrum, which would indicate isolated attosecond pulse generation. Yeah, this part is the attosecond burst, and this is the isolated attosecond pulse. Okay, so this was high harmonic generation. I guess we will probably come back to that once we get to the actual free electron lasers to better compare what are the advantages and disadvantages of each technology. But before that, I think we have to have another look into the good old X-ray tube, which is like the most the oldest and most established source of generating X-ray radiation. Just a little recap on that, because X-ray tubes are actually still being used not only at the dentist, but also for scientific applications. And one reason to still use these X-ray tubes is that actually their efficiency is quite decent. We're talking about 1% of conversion efficiency of, in this case, electrical power into X-ray generation, which yeah, easily provides 100 watt or even kilowatt of X-ray power by very simple means. Yeah, no lasers, just an electric power supply, okay, high voltage power supply, but which is much cheaper than buying one of these femtosecond lasers, for example, that we just talked about. Yeah, and I mean, I'm sure you're all familiar with how an X-ray tube works. I mean, it starts out with thermionic emission of electrons out of a heated filament, where the electrons are then accelerated by high voltage, high potential difference between the cathode and an anode material, which is typically tungsten or some refractory material here. And then the electrons, by impacting on the solid material, get negatively accelerated, and this acceleration of a charge of the electrons always leads to emission of radiation. And in this case, the typical emission spectrum has these two components. That has sharp characteristic lines, which are indicative of like transitions between discrete states in the atom, like typically K alpha or the K shell recombination emission. And there's a broad distribution due to what is called Bremsstrahlung, just the fact that the electrons are accelerated when they hit into the material and just directly emit radiation from hitting the material. So yeah, that is the typical X-ray tube radiation. Just to mention that this type of X-ray tube was actually very important even in the early days of X-ray science, like in like the famous Max von Laue diffraction experiments, which were carried out by Friedrich and Knipping in Germany, actually not so far away from here. They relied on an X-ray tube already more than 100 years ago. And even in this experiment where the X-rays were emitted in a incoherent, and this incoherent fluorescence and Bremsstrahlungs emission process, it was possible to actually produce a rather spatially coherent beam by just spatially filtering the radiation by passing it through a slit and then sending the beam onto a crystal. And in this way, it was possible to detect these diffraction images, like these characteristic Laue peaks in the on a screen, which then enabled the people back then to infer on the crystal structure of the sample. And those copper sulfate in that first experiment. Nowadays, this method is used both for diagnostics at the dentist or at hospitals, but also for radiotherapy. It's actually quite an important method for cancer therapy. Only that there, typically, it's not KeV radiation, but we are talking about mega electron volt radiation. And for therapeutic applications, we need powers that are much higher than the typical radiation, like X-rays for diagnostics. So here we're talking about 100 watt up to kilowatt of time averaged output power of these particular types of X-ray sources, which are operated typically in a pulsed mode. So typically it's they produce pulses between 3 and 5 microsecond at a repetition rate of 100 to 400 hertz, where each pulse actually has a peak power of up to 10 megawatt. So this is actually quite impressive in terms of X-ray pulsed sources that are quite widespread, and you can find these in hospitals. The technology behind is that, again, electrons are produced from a thermionic emission from a filament, and then these electrons are accelerated along a linear accelerator, just driven by high voltages, by this cascade of high voltage acceleration stages. And then the electrons are guided through magnetic fields and eventually hit a thin metal target This is typically tungsten or molybdenum or so, where the X-ray radiation is produced, and this radiation then irradiates the patient for cancer therapy applications in this technology. All right, maybe I would say, let's quickly wrap up this part, and by recapping what kind of transitions we have considered for now. So in general terms, we can group these different sources of radiation into what is called bound-bound transitions. So bound-bound means this is transitions between bound levels in atoms or molecules, represented by the transition labeled 1 here, for example, a transition from the second excited state down to the ground state. These bound-bound transitions are the ones that are driven in spectral lamps, in lasers. Also, the characteristic lines in X-ray tubes are bound-bound transitions, or in laser-driven plasma sources that we discussed. There is characteristic line contributions like this famous 13.5 nanometer line that is used for photolithography. That's a bound-bound transition in tin. But there's also the possibility of having free bound transitions. Free bound, that is represented here by these arrows labeled number 2, where an atom is like kind of ionized. The electron is emitted into the continuum, but then driven back and recombines into a bound state. This kind of transition also emits radiation, and that's what is used in high harmonic generation, where we have this 3-step model. The electron is elongated away from its core, and then recollides, driven back by the electric field of the laser pulse, and recollides, recombines, emits radiation. This type of radiation is also present in plasma sources. And essentially, but fundamentally, there's also the possibility of driving free transitions. So free transitions would be transitions somewhere out in the continuum. And obviously, these type of transitions would offer much more freedom in controlling the wavelength or the photon energy. Because all these bound, free bound transitions are essentially, partly at least, given by the characteristic energy levels, which are fixed by the specific atom or molecular system that we choose. But free transitions would be completely free to tune the photon energy. And actually, this is what we want if we want to build this ultimate light source that is freely tunable and very intense, very bright, and short pulses and all that. But if we want freely tunable radiation, then obviously it should be free transitions. And that's exactly what is the basis of synchrotron radiation and free electron lasers. And I mean, free transitions actually also happen in plasmas, like the Bremsstrahlung, the electrons which are accelerated or decelerated in a plasma, or when they hit back into the solid state material in X-ray tube. This is also free transitions, but rather uncontrolled. We want to drive controlled free transitions. And that's this part of the lecture. Should we have a short break, or should we just keep going for a little while? Maybe some of the organizers could could say a word. I mean, I could benefit from a few minutes break.
Yes,
Or
Marcel, we can take a 10-minute break or a 15-minute break, right, students? Okay, let's do that then.
okay, should we carry on?
Yes, Marcel. Tanuf, is the recording on?
Yes, I'm just starting the
Yes.
YouTube stream back up.
Hey, you should tell us
Yeah,
so that it starts with the recording. Yeah.
so the
I
recording
hope we
just
were not
started.
we were not recording the break, were we?
No, I had posted.
Okay, thanks. Not that we said anything that couldn't be recorded, but still.
All right, then yeah, welcome back
Alrighty.
for the next. How long? Just to have a brief idea, is another 30, 45 minutes, or how much time do we have? When are you
Yes, Marcel.
going to
30
fall
is
asleep?
okay.
30 minutes, okay.
Yeah, it's 8:30, so
Yeah.
9-ish is okay. Yes, Marcel.
All right, then this is the good night speech for you guys.
Yeah,
Fairy
absolutely.
tale. So yeah, we just realized that so far we have been talking about bound-bound transitions, like in standard lasers, free-bound transitions, like in high harmonic generation. But yeah, the best process for having full flexibility in terms of photon energy would be to drive controlled free transitions. So transitions of electrons in the continuum such that we can like freely control the length of this arrow, meaning the photon energy in completely free way. And this is really the basis of synchrotron and free electron lasers. And this is now what we will be talking about from now on. So this is a schematic representation of a synchrotron, as synchrotrons are being used in many places over the world, including India. There's the Indus synchrotron also in India, which relies on electron beam, where the electrons are trapped in this circular orbit, or at least it doesn't have to be fully circular, but at least it's a closed orbit to recycle electrons and hopefully collect electrons and like confine electrons in closed orbit at high density so that we have a large number of electron emitters to emit light in a like intense light and also ideally in a coherent way. So yeah, that's what we ultimately want to reach, intense coherent emission of radiation and even with full degree of control of the photon energy. So to store electrons in these circular orbits, yeah, this relies on accelerator technology. So typically the electrons are confined in magnetic fields to bend them around the corner in bending magnets. The electrons have to be focused in focusing magnets. They have to be constantly accelerated to compensate for energy loss that they experience from irradiating radiation. All these components have to be implemented in these storage rings. And in order to now have the electrons emit radiation in a controlled way, meaning at the controlled wavelength and ideally also with controlled intensity, these storage rings contain what is called insertion devices. And these insertion devices, these are magnetic field structures which force the electrons to move on accelerated trajectories such that by accelerating the electrons in a controlled way, the electrons would emit radiation. Yeah, as you know, any accelerated charged particle emits radiation. And by controlling the acceleration and the direction of acceleration. In principle, we can try to control the emission of this synchrotron radiation. And then once this is achieved in this insertion device, the radiation is outcoupled from the storage ring and then guided into what is called beam lines. A beam line is an arrangement of then X-ray optical components like a monochromator to further monochromatize the radiation, meaning to select out specific photon energies, to focus the radiation on a sample and then do an experiment in this beam line. So that's the general concept of a synchrotron. And one example that I have to show, because I had been working at the Aarhus University in Denmark. So that's a university that has its own small-scale synchrotron in the basement. And I'm continuing to use this synchrotron facility. And this is a small one, but yet quite a well-developed one. Is shown here. So this one is driven by electrons at an energy of about half a giga-electron volt. This is rather low energy. Usual large-scale synchrotrons work at electron energies more in the giga-electron volt range. It is 45 meters in circumference, has a typical electron current in the ring, meaning that this is the current in milliamps, 200 milliamps of pure electrons orbiting at almost the speed of light inside the storage ring. They are radio frequency accelerated and so on. The typical arrangement consists of these two storage rings actually. So the main storage ring is this one to the right. That's where the electrons are kept on in a stationary orbit and continuously irradiate light in the insertion devices. For example, the device up here, that's a so-called undulator, which forces the electrons to undulate, like to perform oscillatory motion to emit radiation along this beamline that would travel over there. So that's the main storage ring that operates at constant electron energy, in this case 580 mega electron volts. But then to get the electrons to this quite high energy, the electrons have to be pre-accelerated, and like all these modern synchrotrons have at least one what is called a booster ring, which is a first accelerator ring here, which pre-accelerates the electrons to this final energy. And then electrons are actually injected into the main storage ring in a periodic fashion. Every time a bunch of electrons is accelerated up to this final energy, then this bunch is injected into the main storage ring, where many of these bunches are then kept for a long time on these stable orbits and stationary orbits at constant energy. So that's what is an example of a small-scale synchrotron. There's many large-scale synchrotrons around, like this one, Soleil in France, near Paris. You can see that I mean, the concept is always the same. There's the main accelerator ring here, which at Soleil it's operates at 2.75 giga electron volts. There's this first or this booster ring, which brings the electron up to this energy, and actually even this booster ring has a pre-accelerator, which is a LINAC, a linear accelerator, to get the electrons from the electron source up to around 100 mega electron volts. So the electrons are actually injected into the booster at 100 mega electron volts, and then the booster ring is operated in the actual synchrotron mode. I mean, synchrotron, from the name, you can guess that something has to be synchronized with something else. And what is synchronized in a like the traditional synchrotron is the acceleration, like there must be some accelerating structure inside this synchrotron ring. But as the electron energy in the actual synchrotron ring is accelerated, also the magnetic fields to confine the electrons need to be enhanced, because a higher energetic electron needs stronger electric fields to be kept on the same closed orbit. So it should, like the actual synchrotron concept relies on synchronously ramping up both acceleration and the confining magnetic field. So that is how the booster is operated. And then this, of course, only works in a periodic pulsed way. So every time a bunch of electrons is boosted up to the final energy of from 100 mega electron volts to 2.75 giga, then this bunch of electrons is injected into the main storage ring, where then the electron is kept on a closed orbit for extended periods of time. Yeah, just to give you a brief overview of the historical developments that led to these synchrotrons, which are nowadays like really a very important technology, both for research purposes, but also like there's beamlines that are fully operated by private companies for material science, for crystal structure analysis, for example, material science analysis, and like not only fundamental research, but also industrial applications. Just to give you a brief overview of the historical developments. Basically, it started out from the list of these different events and names. Maybe I picked this one here, which maybe it's worth remembering, which is Macmillan in the US and Wechsler, which basically in the same year have independently proposed the synchrotron concept to reach high energies, by this synchronous ramping of energy and confining magnetic fields. And then an interesting fact maybe to be aware of is that the first generation, what is called the first generation synchrotrons or synchrotron radiation sources, were actually basically measurement end stations placed at accelerator structures, which were designed for nuclear research or particle physics research. So where they were actually, these accelerators in the beginning were not at all designed as light sources, but for collision experiments. But like clever photon scientists in the 60s and 70s of the past century figured out that these electrons and positrons that were accelerated to high energies and then bent around the corner in the bending magnets, or passing through some oscillatory magnetic structures, actually emitted radiation, which was an unwanted effect for these particle physics people, because they wanted just high energetic electrons and other particles for collision experiments. And they didn't want, basically, it was an unwanted effect for these particles to lose energy by irradiating synchrotron radiation. But on the other side, the synchrotron radiation turned out to be quite useful for all sorts of spectroscopy experiments, for example. So then only what is called the second generation synchrotron radiation sources then were actually dedicated dedicated accelerators for generating synchrotron radiation for X-ray science. And since this was very successful, and even like in India, the Indus 1 and 2 are still operated, categorized as second generation synchrotron sources. These synchrotrons have been further developed into third generation, which essentially means much higher brilliance. So brilliance is a quantity that characterizes both the photon flux, like how many photons per square meter per second, but also per beam divergence in millirad square. And even it contains information about the bandwidth, like the spectral bandwidth. So high brilliance means high photon flux in a low divergence beam and at a small spectral bandwidth. And essentially, since then, the newer generation synchrotrons have always improved on, oh, this should actually be 10 to the 20, not 10 to the, so it was 10 to the 20 photons per second in the third generation, and nowadays, fourth generation is 10 to the 22 brilliance. And there's only a few of these fourth generation synchrotrons around. One of them is Max 4 in Sweden, where Shiva and I have actually participated in experiments already. There's a European synchrotron radiation facility in Grenoble in France, which is fourth generation. There's the advanced photon source in the United States, and I think a few more. So that's the synchrotron newest synchrotron sources. So synchrotron science is still developing, and the main reason is that these synchrotrons are so extremely versatile. They can be used for so many different applications and fundamental science that although it's a technology that dates back to the, let's say, 1960s and 70s of the last century, still new synchrotrons are being built and constantly improved just because it's of their large versatility, and also, as you can see, because they are very efficient. Yeah, the infrastructure, the storage ring can be used for how many? 25 beamlines or 29 beamlines. This is already 10 years ago. And that these 29 beamlines operating at the same time, simultaneously, which makes these facilities very efficient and very productive. But there is new developments, and the next generation synchrotron source, in quotation marks, is the free electron laser. It relies on basically on the same basic principle, but we will see that there is some very specific new features. In particular, the way of building these free electron lasers is different. All these standard synchrotron sources rely on storage rings, where the electron beam orbits around on a closed orbit, whereas free electron lasers rely on linear accelerators. But let's stick to synchrotrons for a little while. And the very first, very simplest synchrotron radiation sources, which were explored as parasitic light sources in the beginning. I mentioned that it started out from using synchrotron radiation emitted from particle accelerators that were actually just meant for particle physics. But so the simplest way of producing radiation in these accelerator facilities is just by bending electrons around the corner in what is called a bending magnet. So these are just dipole magnets that are needed for closing the orbit in the storage ring. But obviously, these electrons that are accelerated laterally to move around the corner still are being accelerated. Accelerated charges emit radiation. So every bending magnet produces radiation. It's not very controlled or specific, meaning that the emitted radiation spectrum is rather broad. You can see here, this is a bending magnet spectrum for an electron beam at 3 different energies, 2, 4, and 6 gigaelectron volts, and also different magnetic field strength. Obviously, the higher energy produces higher energetic radiation, and also the higher magnetic field produces a higher photon energies, because higher magnetic field means a stronger deflection of the electron beam due to the stronger Lorentz force, and stronger deflection means stronger acceleration, means stronger emission and more energetic emission of radiation. So yeah, the general concept of these synchrotron storage rings is illustrated here. So there's so usually they are not perfectly circular, but they have this discrete bending magnet sections, where in each bending magnet radiation is emitted. And in addition to that, in the linear sections, we can install dedicated insertion devices, mainly wigglers and undulators, which can emit radiation in even a more controlled way than just these bending magnets. And this is actually a photograph of such a dipole magnet mounted around the beam line. Of course, the electrons travel inside vacuum in these vacuum tubes, and these quite big and bulky magnets are mounted around the vacuum pipes to produce strong magnetic fields and deflect the electrons around the corner. So traditionally, these bending magnets are just electromagnets. So you can imagine they consume a lot of energy. Nowadays, these magnets actually can be replaced by permanent magnets, or combination of permanent and electromagnets, which greatly reduces the energy consumption, which of course is becoming more of an issue nowadays. Yeah, so bending magnets, this is the simplest way of producing radiation. Actually, it turns out the radiation from a bending magnet is still confined in a kind of beam-like, rather low divergence beam, where the divergence angle is given by gamma. Gamma is the relativistic factor. So for higher energy of the electron beam and a larger gamma, the larger the gamma, the more relativistic the electrons are. Actually, the more beam-like the light is that is emitted from such a bending magnet. Obviously, a straightforward extension of this bending magnet concept is to just let's say, put several of these magnets in a row to just add up the radiation emitted in every magnetic bending section. And this is exactly, this arrangement is called a wiggler. Yeah, so just a periodic arrangement of magnetic fields that are periodically poled, north-south, south-north, north-south, and so on, in a way that the radiation is in every bending section is like superimposed into a macroscopic beam, but in an incoherent way. So the Wiggler radiation spectrum essentially looks very similar as the one of the bending magnet. Of course, it's more intense because all these bending sections add up, and but also the divergence angle is very similar to the one of a bending magnet. There's a parameter k that comes into the play here, and we will see in a few minutes what k is. The next generation and much better way of producing synchrotron radiation is what is called an undulator. The basic principle, again, is just a periodic arrangement of bending magnets, but in this way, actually, the elongation of the electron trajectories in every section of, like in every element of this undulator is so small that the emitted light from every element superimposes and interferes with the light emitted from the next period in the undulator. And then it comes to choosing the energy right of the electrons and designing this this undulator structure correctly to assure that the light that superimposes in each period interferes constructively. And whenever constructive interference occurs, then we may expect a strong spectral component in the spectrum. Whereas when there's no, like for those photon energies where it doesn't match the periodicity of the undulator, there's destructive interference and no radiation is emitted. So just from this concept of interfering partial beams created along the undulator, we can already understand that the spectrum of such an undulator comes in this periodic feature or this periodic structure with first order and then higher order constructive interference. And another advantage, besides the very sharp narrow band emission spectrum of undulators, is that also the divergence angle of the undulator beams is much lower, which is essentially now it scales. It does scale like 1 over the gamma relativistic parameter, just like the other two sources. But in addition to that, there is a factor of 1 over square root of n, where n is the number of undulator periods. So obviously, if we build the undulator very long with many undulator periods, then this helps to reduce the divergence angle and to get even better collimated beam. Yeah, the typical undulator period, which is given by the actual geometric spacing between permanent magnets that are periodically poled, like this in the simplest way. The undulator period is on the order of 2 centimeters. And if we want to have some degree of control of like the forces acting, the Lorentz forces acting on the electrons here, we actually would like to control the magnitude of the magnetic field. But since we want strong magnetic fields, which are most conveniently generated by permanent magnets, and permanent magnets cannot be controlled in their magnetic field, the only way of having a knob for controlling the magnetic field is to actually mechanically change what is called the gap between the poles of the upper and in the upper and lower array of permanent magnets. So this the undulator gap is always a very important control parameter that needs to be mechanically controlled very precisely in these undulator structures. And on the right-hand side, you can see a typical such a mechanical device that contains all these many precision mounted permanent magnets, and all that heavy arrangement needs to be moved very precisely up and down to control the gap between the magnets. And typical dimension is like 2 meters or so for a typical undulator in a synchrotron. So these are quite bulky mechanical devices that need to be controlled very precisely. Yeah, and then, I mean, you may wonder, okay, the undulator period is on the order of 2 centimeters. And I mean, the electrons that now fly through this periodic field arrangement would likely emit light that then oscillates at 2 centimeter wavelength, right? But 2 centimeter wavelength, this is, what is this? This is microwaves or so. This is very far away from the X-rays that we would like to have. Yeah, if we want to have X-rays, X-ray have a wavelength on the order of angstrom. So somehow we have to get from these 2 centimeter periodicity given by the undulator down to the angstrom wavelength regime. And turns out that this is actually given that, so this transformation from centimeter like undulator period length into angstrom wavelengths is given by relativity, by the fact that these electrons move at nearly the speed of light, and then by the mysteries of special relativity, we get a wavelength reduction of 8 orders of magnitude. And we will see how this works in just a minute. So the basic principle is accelerated charges, or charges that are accelerated in this periodic fashion, just like electrons in an antenna move up and down along the conductive rods of the antenna. They would emit dipole radiation in this Hertzian dipole emission pattern. So this is the starting point of the synchrotron radiation emitted by the electrons wiggling up and down as they fly through the undulator. So the procedure is that in the lab rest frame, electrons are forced on this periodic trajectories through the undulator. But the electrons are relativistic, so their energy is given by this relativistic formula, gamma times mc square. M is the rest mass of the electrons. Remember, the rest mass of electrons is 511 kilo electron volts over c square. And gamma is the relativistic factor given by 1 over square root of 1 minus v over v square over c square. And then we have to see what happens for the electrons in their rest frame. And that is given by the Lorentz contraction, where then the wavelength that the electrons see in their rest frame is actually the undulator wavelength divided by a gamma, relativistic gamma parameter, which we really have to figure out more in a more close calculation. And then in the rest frame of the electrons, they perform this oscillatory motion and would emit the Hertzian dipole radiation with this sine square theta angular dependence. But this is the radiation pattern in the rest frame of the electrons. Eventually, we have to transform back into the lab frame because the experiments in the end take place in the lab frame. So this transformation back into the lab frame then actually introduces another factor 1 over gamma, which in the end gives us a scaling of the radiation wavelength as the undulator wavelength divided by gamma square. And now by just having gamma, which depends on the velocity of the electrons, or the velocity over speed of light, if that is fast enough, then gamma is large enough to reduce, to bring down the undulator wavelength from centimeters down to angstrom wavelengths. That's the goal. And in addition to that, so special relativity has actually two beneficial effects. One is this contraction of the wavelength by 1 over gamma square. The other effect is that also due to the fact that electrons move at relativistic speeds, if we do the Lorentz transformation back into the lab frame, we see that the Hertzian dipole emission pattern in the rest frame of electrons actually transforms into a highly forward peaked emission pattern. So down here you see that the velocity of electrons v over c, if it's slow, if it's low, 0.01, it's just a dipole pattern. As we approach the speed of light, then the emissions pattern gets very much forward peaked, and this is also called the relativistic flashlight effect, which helps us to get a beam out of the bending. That's at the origin of the beamline emission pattern, even from the bending magnet. So a little exercise for you just before going to sleep. Given that an electron beam is accelerated to 5 giga-electron volts, that's quite high, but yeah, I mean, this is on the order of what electrons are typically accelerated to in these synchrotron devices. What's the gamma factor? How large is it? Can anybody tell me? Like, yeah, gamma is really the control parameter that controls everything in this game. For example, how short the wavelength will be, because I mean, undulator wavelength is fixed by the permanent magnets, and like the construction of the undulator, this is fixed once we have built the device. But there's still gamma to tweak the wavelength. So how large is gamma for an electron beam that's 5 GeV in energy? Okay, I guess you need the information about this MEC square. I just told you, ME.
Approximately 10,000.
Yes, exactly. Just divide by 0.5 GeV. So 5 divided by, or 5 GeV divided by 0.5 MeV. That's a factor of 10,000. So what's then the wavelength of the emitted light? The actual formula is undulator wavelength divided by 2 times gamma square. Lambda, the undulator, that's the undulator period. How long was the undulator period? That was on the previous slide. Lambda, the undulator period is, yeah, this is about the length of these permanent magnets, 2 centimeters. So 2 centimeters divided by, conveniently, there's this factor of 2 gamma square. 2 centimeters divided by 2 times gamma is 10,000, so it's 10 to the 8. So 1 centimeter divided by 10 to the 8. 1 centimeter is 10 to the minus 2 divided by 10 to the 8 is 1 centimeter, 10 to the minus 8, 1 angstrom. So that's where we want to go, right? That's X-rays. 1 angstrom is just the typical bond length in solid states. So if you want to do solid state diffraction, or we want to study individual atoms in a crystal, we need to reach this 1 angstrom range of wavelength. And that's what we get from relativistic electrons. Okay, then I think we have to go through a little bit of math to really understand how this comes about. So the starting point is the electrons flying through the magnetic fields at relativistic speeds. In the magnetic field, they experience a Lorentz force. In principle, there's also electric fields around, because I mean the electrons emit light, and the synchrotron radiation has an electric field, but in synchrotrons, typically this electric field is very small compared to the magnetic field. So in synchrotrons, we can ignore the electric field. This, however, is no longer the case when we come to free electron lasers. We will see that in free electron lasers, the main difference compared to synchrotron sources is that the electric field emitted by the electrons can no longer be ignored. And actually, the electric field emitted by the electrons will backcouple onto the electron motion and influence the electron motion, and in that way produce like a self-amplification, like self-amplifying loop of increasing the emission of synchrotron radiation in the free electron laser. But for now, In the synchrotron, we can ignore and just consider the magnetic fields. And if we set our coordinate system such that the z-axis is along the electron beam direction, and then we have the y-axis going along the magnetic field direction, and the x-axis perpendicular, then by writing out the cross product of velocity cross magnetic field, I mean, just you can do it for yourself. You have to write the determinant unit vectors, v, b vectors. If you spell it out, we will see that there is only the x component and the z component left, where the x component has vz times by and the minus, and the y component of the dp by dt is vx times by. So the z component is bx by dby. So we get two differential equations. I mean, derivative of velocity is the double derivative of coordinate with respect to time is vz is z derivative, and we divide by gamma m. We have these two equations. If we divide first equation by the second equation, so x dot dot divided by z dot dot, we multiply this, cross multiply the equation, we get this, and this can be written as like derivative of z square plus x square. Yeah, I mean, if we take the derivative of first derivative square, we get 2 times first derivative times second derivative on both sides, and so that the 2 cancels out. So this we get. So which means that the magnitude, like the total speed, which is given by this by the sum of the squares here, is constant. So meaning that the oscillation in the x direction, that's like perpendicular to the propagation of the electrons, slows down the motion in the z direction. Okay, next we have to consider the magnetic field, which is periodic.
So Marcel, sorry to disturb. Like, actually, we have this meeting scheduled till 9:15 India time, and it's only 1 minute
Yes.
left. So we have sent a new link which extends till 9:30. So might be we'll have to change to that link after this, once this meeting stops. We can continue for like 15 minutes. That shouldn't be a problem.
Yeah, I mean, it's fully up to you. If you want to continue, we continue. We could also stop here and then just continue next week. It's up to you. If really, and this will go on for a little while.
Then we can shift to another link. We actually shared one more link in the calendar just now. That will extend for like
No,
15
it's
minutes.
the same link. It's the same link. I
Same.
just extended the meeting to 9:30.
Okay, fine.
Okay.
Then fine.
So should we restart the session then?
No, you can continue with this.
Okay, great.
Yeah.
Okay, then, I mean, if we have another 10 or 15 minutes, then I think that should just be enough to go through these derivations and end up with an important formula that we will be using throughout a lot. So yeah, this is a bit of math, but I think the derivations are quite straightforward and will lead to an important result. So the magnetic field is given by this periodically poled undulator structure. So we can, but of course it's the magnetic field as the electrons fly along the z-axis is not just a sine wave or so, it's pretty much given by a square shape, right? Because inside the poles of one this unit, we have more or less a homogeneous magnetic field, and then suddenly, as the electron flies into the next period, we have another more or less homogeneous electric field. So it definitely will contain, if we take a Fourier series of this magnetic field, it will contain some higher harmonics, but we can always do an expansion into lower orders and mainly consider the magnetic field as a cosine of 2 pi z divided by the undulator period or the undulator wavelength plus higher orders, which we conveniently ignore. And now, if we now substitute, this so this was the expression we got just before for the double derivative of the motion of the electron along x. That was the expression just from the slide before here, written here. So I kept it on that slide. And this expression we now substitute into, let me see. We now substitute the by from this series into the by in this formula. Then we arrive, and we just consider this first order expansion. Then we arrive to this expression. And that the first derivative of z times cosine z can be written as a derivative of sine of this expression, right? Because the first derivative of sine of a coefficient times z is outer derivative, gives the cosine, times the inner derivative gives the z dot. So we have just one derivative of a function. We integrate once to get from second derivative of x to first derivative of x, and the derivative in front of the sine function disappears. So now we have an expression for the velocity in x as a sine function with this undulator periodicity. And that's an important result. And in particular, the prefactor here, this prefactor has its own definition. So EB, undulator wavelength divided by 2 pi electron mass times speed of light, that is called the undulator parameter. And that's an important parameter. In particular, for undulators, this is usually a number smaller than 1. But if k is larger than 1, then we talk about a wiggler. And if you remember, the wiggler is very similar device, but where the electron oscillations have a large amplitude such that the partial beams emitted actually do not superimpose. And there was no interference happening in the wiggler. But obviously the undulator is the more interesting device because there we have interference, we get these narrow band emission in first order, second order, and so on. Okay, so that was a derivation of the term the velocity of electrons in the transverse direction. Now let's look for the derivative along the z direction, so along the propagation. So there, we use the relativistic parameter, which so we can rewrite this in where v square is the initial velocity of the electrons entering in the whole undulator. So we can rewrite the formula in this way, and just change the order of the terms. And that was the formula from just before with the definition of this k, the undulator parameter. We get this expression, and that knowing that the electrons are highly relativistic, so the gamma parameter is large, we can rewrite this in the following term, in the following way, by basically by expanding the square root. If we take the square root of this expansion, square root of 1 plus small terms. I mean, gamma is large, so 1 over gamma square is here, 1 over gamma square. These are small terms. The expansion of a square root of 1 plus or minus a small term is 1 minus half of these terms. And we get these expressions. And yeah, that in particular, we get this, like the sine square term can be also written in cosine of half the at half the argument, and that interestingly actually gives a component of the emission of radiation in the perpendicular direction of this first term. Yeah, so this gives a cosine term emission in the perpendicular direction. Yeah, so additional harmonics generated are generated with opposite polarization to the main emission pattern. Yeah, but if we take the time average, then the oscillatory term cancels out, and in the time average, we are left with with such a formula. And now in this third step, we have to find this correct gamma factor that is needed to transform into the rest frame of the electrons. And yeah, this gamma is 1 over the, like is the formula for gamma, but with the this time average expression here. So if we now inject this expression from the previous slide, this one here, into that expression, and again we assume that gamma is large, so we expand the square expression up to the first order. Then there's just a factor of 2. That's just binomial formula, and we keep the linear term. The factor of 2 comes in front. We get this expression. So that gives us the proper relativistic gamma parameter that now includes the undulator parameter here, which basically takes into account that the electrons do not fly just along a straight parameter, but actually perform this undulatory motion. So light emitted in the co-moving frame, in the electron rest frame, there we get this first Lorentz compression of the wavelength, but according to the relativistic parameter gamma star, that includes this undulator parameter, taking into account that it's not a straight trajectory, but an undulatory motion. Okay, so we are in the rest frame of the electron. Now next, we have to, on the last step, we have to transform back into the rest frame into the lab frame. And yeah, so this takes into account that the electrons basically move towards the receiver, and the general formula is this one, where we have these different like wavelength and gamma parameters that we just derived. And if we plug this all in now, we get quite a lengthy formula for the wavelength that now eventually is measured in the lab frame. After these like 2 Lorentz transformations, that can be written in this way, and maybe to cut it short and finally arrive to the main formula here. So this is the undulator equation. So if you remember one thing, then it's this from this whole discussion, then it's this undulator equation, which determines the wavelength measured in the rest frame in the lab. Sorry, the wavelength in the lab frame. So what is really measured as a function of the undulator period or the undulator wavelength and the gamma parameter, which is given by the electron energy. And important, if you want to remember only a short formula, then it's the first term here, which is the leading term. And that's the term that we discussed in the very beginning. Yeah, that due to this back and forth transformation, we get 2 times a multiplication with 1 over gamma. So this 1 over the gamma square comes into the play, and that contracts down from the undulator period down to the, which is like centimeters, to the actual wavelength of the radiation, which is angstrom wavelength. But there is extra terms, namely the undulator parameter here. And there's this extra term that depends on the emission angle. Yeah, and what important is that basically there's 2 control knobs if we want to tune the wavelength of the light. There's 2 control knobs. One is, of course, the energy of the electrons that is that determines the gamma parameter, but also the magnetic field strength. And remember, the magnetic field, even if we have this permanent magnet arrangement, we can still control the magnetic field just by mechanically changing the gap between the north and south poles, and in this way have like a second control knob to fine tune the wavelength of the emit light. But there's also a angular dependence, and this angular dependence means that if we look away from the beam axis, we will measure slightly different emission spectrum. Yeah, so as we, is this the right? Yeah, so the emission spectrum is slightly different for between, and is most energetic at 0 angle, but as we move away from the 0 angle, so from the beam axis, we will see a slightly changed emission spectrum. So yeah, this is important to keep in mind if we have an extended sample, for example, that would cover a larger extent of the beam, then we have to keep in mind that the light might not be like fully monochromatic, but may contain more frequency components. All right, maybe this is a good time to. Okay, maybe this is a good time to finish off for today. So this undulator formula, that's an important formula that contains these gamma and so on. There's a simplified version. Basically, we have to remember only the undulated, it depends on the undulator period, the energy in GeV, and then there's a factor of 13 if we actually plug in numerical values where the undulator length is given in centimeter and energy in GeV. So this is, let's say, a rule of thumb that can be used for just estimating what the wavelength of the radiation should be. Plus this extra term containing the undulator parameter, which is typically for undulators smaller than 1. Okay, I think maybe this is a good moment to stop, and we continue a little bit with the discussion of undulators then next week, before then presenting some applications of synchrotron radiation. So we have an idea of what we can do with just synchrotrons already, and then to get prepared for discussing how free electrons lasers actually work, and then what new type of experiments we can actually do with free electron lasers that we cannot do just with these synchrotron radiation sources. So then I would say thank you very much for listening. This was quite some math, but I think the main point was to get to this undulator equation and to show you that all these derivations are rather simple and straightforward, and essentially rely on special relativity and on the fact that electrons are relativistic and have to transform back and forth from the lab frame to the rest frame and back to the lab frame, and we get to this formula. So thank you for your attention, and there will be an announcement, I guess, about the next session on Friday, which will be just for you to get prepared to do some simulations of the free electron laser principle. This will go along with the lectures then continuing next week. Thank you for your attention, and have a
Well,
good
thank
evening.
you. Long session, you must have prepared a lot.
Yeah, very welcome. It's instructive for you guys and for me just as well, I can tell you.
Really
And
nice
for
compilation.
people. Yeah. Thanks. Then yeah, have a good night and see you very soon.
See you.